Hello and welcome to a revisiting of Module 6. I thought I'd go back and cover it again, primarily because it's one that people haven't finished. So we'll also talk a bit about Deliverable 7 as well. So jumping straight in, what's Module 6 about? And it's around validating a statistical model. This is probably something you've talked about and heard about in other courses. Hopefully it's a review. If it's not, well, it's a good time to learn. So we'll basically talk about the concept of holdout sampling, and then we'll talk a little bit about cross-validation and k-folds. So a common pattern whenever you're dealing with any kind of machine learning is to separate things out into different sets of data. There's at least, generally speaking, 2 sets, sometimes 3. So you have a training set and a test set. Those are the very common ones that you'll utilize. And you have to be really careful whenever you're doing some of this type of work, because you can sometimes inadvertently expose your model to your test set, something that you should never do until you're actually doing the final calculation of accuracy or performance. So there are ways to avoid doing that, including potentially pipeline type architectures where you define the order in which processing occurs of your various operations, and so you're certain what's happening where. In addition to the training and test sets, you have this concept of a validation set. So training set, that's kind of self-explanatory. It's what you train the model with. That's whenever you're essentially determining fit. So you're doing the tuning of something inside of the thing. If you're dealing with neural networks, you're adjusting weights. If you're dealing with statistics, you're potentially similarly somewhat adjusting weights depending upon the algorithm you're using. But you're basically trying to essentially fit, you think of it as the expression to the data. And so validation's slightly different, and that's where you're dealing with tuning your hyperparameters. So the basic idea of validation is that you can see what happens whenever you're making changes along the way, and you may very well use it to essentially assess how well it's doing. So for example, if you're doing some sort of neural network training that has a series of epochs, which is a fancy word for just an entire pass through all the data, right? You may at the end of each epoch want to calculate how well it's done. That's where your validation set comes to play. And part of the reason you do that is that you want to stop when you reach a certain point. Otherwise you might you may actually make it worse. So it's one of those kind of counterintuitive things that sometimes if a little does a little good and a lot does a lot of good, kind of logic doesn't hold up. So that's where you want to use the validation set to essentially determine how much loss you have going on, what's the overall performance of the model. Is it good enough? Because if it's good enough, you probably want to stop. That's something else to consider. So this is a very common sort of pattern and something to keep in mind. You also typically need to have some metrics to back what it is that you're making your determination. Before you start doing stuff, you need to figure out what's your success criteria. This is true in life in general, but especially true in machine learning and data science. So you definitely want to figure out what good looks like. So what measure, what formula, what calculation are you going to utilize to determine essentially how good something is? And ideally you should start this early on, even before you start even gathering data. It should be part of kind of your problem statement of what is it you're trying to address. And by doing that, you're able to say, by addressing this, I can also determine what's good, right? So you can basically say, at the beginning of the experience, we will know we have succeeded if we hit 80% accuracy or 90% accuracy, and accuracy being defined in a very explicit way of what that means and on what sort of data. You'll also have this the concepts of using accuracy F1, area under the curve, and so on. In particular, receiver operation characteristics, ROC, and area under the curve. It's pretty commonly used, and it's something that is also important. Something that I may talk about, if time permits in this course, around automated machine learning, so AutoML. If you haven't seen AutoML, then let me know, because I'll show it to you. The gist of it is all that stuff you learned in classification and various other classes where you go and try 20 different models or 5 different models or 3 different models. It does it for you at the scale of thousands of models, adjusting hyperparameters for you and various other things. And then at the end of the experience, because you've told it, here is what good looks like, right? So here is the formula that you're either minimizing or maximizing. It'll tell you this is the solution that you should utilize. And then better than just that, you can then say, okay, deploy that to production, and it'll essentially expose it as a REST endpoint, so you can start using it that quickly. So cool stuff, but it all comes down to knowing your metrics, and that's where, at very least, you need to understand what they mean, ideally how you calculate them, but more, what does it mean and what's significant, what is good little, or good bad, whenever it's big. So figure those sort of things out. When we're talking about models and model evaluation, it goes beyond simply accuracy. That's obviously important, and you definitely are going to want some things where there's predictability. That's probably not on here, but consistency, I guess it is. So you definitely want things where there's some transparency in your model, and that's, you start at the bottom, work your way up. You want to make sure that it's you can interpret the results of the model. You can explain, or the model can explain why it's doing what it's doing. And that's where things like decision trees and random forests sometimes can come out to be pretty useful, because they're almost self-explanatory. You need to understand if it's clear and if it's consistent. If it consistently and also reliably predicts the same sort of stuff, that's very important. You also want to make sure, obviously, that privacy, security, robustness, and certainty is in the mix, because you want to be able to ensure that these predictions are reliable. And then the lastness around fairness. This is something that's become more emerging and consistently is becoming more emerging around things like diversity and inclusion and justice and equality, and equity. So being fair within our models is important, and sometimes you have to consider what attributes to leave out. That may be counterintuitive, but there's some attributes that you're better off perhaps not including in your model. Race and gender, do they really add any value, and are they a fair thing to include in your model, or are you inadvertently biasing your model to produce something that's not desirable for certain portions of the population? So you have to consider these things whenever you're assessing how well a model is doing. The general steps, whenever you're dealing with pretty much any kind of prediction or classification, is, and it's this pattern fits even regardless of what you're doing most of the time. You start off by obviously loading the data up. Maybe there's a step or two before that where you get access to it, and so on. And maybe there's also a step or two missing here of things like cleanse. I didn't include that. But you load it up, you explore it, you separate your attributes from your labels. Then you typically do the split across the train and test. So set aside a certain percentage for testing. Then, generally speaking, you'll transform or standardize, transform, and fit, those sort of operations. And you may very well do, especially if you're doing things like standardization or transformations, you may do that to both train and test. Then you'll create a classifier and do your fit. So you're basically going to do your training, so to speak, and then you'll use it to do some predictions, and then you do the checking of the accuracy using that test set that you've held back. It's a very common pattern, and it's one that is important to understand, and it is quite relevant and important. So this common approach I just talked about, split the data into a training and test set. You never, ever, 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 ever train on your test set. You don't let anything see it until you're near the end. And that's, if you do otherwise, then you've essentially invalidated your research. So make sure that you set it aside and hold it out, right? It's similar to things like if you're doing a research at an academic level, you come up with a hypothesis. Oftentimes at that same point, you'll come up with what is what you consider to be significant. So you establish your significance level prior to starting the actual process. And then once you've done that, then you actually go do your research. Same sort of concept. After you do the training, you evaluate, see how well it's done, and so on. I heard someone join. I'll take a pause. I'm reviewing Module 6, so be warned, I guess. So if it's not something that's interesting, you don't have to hang out. Okay, maybe it was just my phone doing something weird. All right, moving on. WebEx was acting kind of odd, so maybe that's what's going on. So cross-validation, pretty simple concept in a way, but yet very important and powerful. So the basic idea here, and you'll see the word k-fold, that's the way that you know you're doing cross-validation, is you basically separate your data into k buckets, if you will. And then on each iteration, one of those buckets is your test set, the others are your training set, and you shift buckets as you go through each of the k's. So if you've got k equals 4, as you see in the example on the screen, during the first iteration, iteration 0, the first set is the test set, so you don't let it see it. Then the second iteration, the second item is the test set, and you hold it back, and so on. The basic idea here is to try to increase the amount of essentially data without breaking the rule of letting your model see the test and training set. It's not ideal because you could argue, well, you're showing the model, the test set, just pieces of it at a time, right? But at the same time, there are situations where you have to do this. If you simply don't have enough data, this is an appropriate approach. So it is something to keep in mind. Ideally, you have a bunch of data, you don't have to do it, but sometimes having labeled data is challenging, and so you end up with scarcity. So the basic idea here, talking about that through again, it is a cross-validation that is superior, that results in less bias than other methods. K-fold validation is fairly accurate. It's new, and especially in neural network training processes that provide high level of confidence. And it's pretty good there because it kind of evens out, is what it comes down to. So the basic idea here is to separate into your k different groups, like you have here, 4 different folds, and then on your first split you set aside fold 1 as your test set, and you train on 2 through 4. Second time through, you hold 2 out, and 1 through 1, 3, and 4, and so on. So the basic idea here is that you've increased your amount of training data by a fair amount, right? Without necessarily compromising any of the validity and reducing the amount of bias that might occur. One of the things that you might see, I saw it in some of the stuff I was doing, was sometimes one of those folds may be significantly better or worse just because of the randomness of the selection. So don't be surprised if you see that. So at this point we'll shift over and do it, which is always good. So we'll start off with kind of how do you hold out the stuff. All right, so we start off with, and hopefully this will work. I haven't tried it ahead of time, never a great thing, but it loaded the file. That's a good thing. So we basically are setting up here, and we're going to create a data file, a data frame called DF, and we're going to split eventually across 75 and 25%. You'll see ranges on that. 20 is generally considered the kind of the target you go for, 20/80. You might go down to smaller if n is big, is the argument. So you might hold back less if you've got an awful lot of data. So if you've got 5 billion records, do you really need 20% of that to do the testing? It's a reasonable argument if your sample especially is representative. So it's a reasonable sort of thing. So we can go through here, and we're saying basically that we want 75% of it to be training and the rest test. So we can basically here, you'll see sometimes this random.seed is equal to some number, right? So seed equals 1 in this case. The reason to do that is to get reproducible results. You don't do this for real. We do it here because you want to see the same stuff each time you run the notebook. If you're doing this, the whole point of randomness is for it to be pseudo-random based upon essentially your clock time, right? So you probably want to not have a set to have a seed unless you have a compelling reason. So here we're basically just creating some random data with a uniform distribution. And then we're taking a look at the first 10 records just to kind of see what's going on here. And we're basically, we're assigning if it's train or not based upon this uniform distribution. So we're setting aside essentially a certain percentage of these as going to be the train. And so then we can go through, take a look at the first and last 10. And then here's where we're going to start setting up our train and test. So up here, we basically said create this column that is inclusion in the random set, and then we're doing essentially a Boolean assignment here, as if with a uniform distribution between 1 and 0, if it's greater than or less than or equal to 75, then it's in the train. That's what this is doing. So I misspoke a little briefly there. And so we're basically wanting to be reproducible so that whenever you run this each time, as we're seeing it, that you're getting the same sort of results. Normally you don't want to do that. And so here we're basically partitioning those data frames into 2 data frames, one being chest, one being train. This is kind of the harder way to do it. I'll show you the easy way here in a minute, but this is kind of walking through it at a painful level so you can see what we're doing. Then we get rid of this column that we used to do the split, so we just delete it out of both data frames. So now if we take a look at the train set, these are only things that are training, and we don't have that one that we added. And then here is the test set, and so we can then move on. Some residue where I was doing some probably analysis of it. So now we basically split things, and we now want to separate out our essentially our variables or our features from our label, in this case y. So we're looking for things that are bad, and we're going to make a copy of the training set and set it to dfx, and then we're setting dfy just to be the column of good or bad, and then we can get rid of it out of dfx because we don't want it there, right? So these are only things that let us be able to predict this, and then we can now start through and do some classification. So we're doing our training, we're setting it on our train set, and so now we've created essentially the train. Now we're I was thinking that should be test. Oh no, it's down here. So we're doing something different with this. It's been a moment. Okay, we're making a copy of our df train, and our setting it to x and y. We're getting rid of bad again, and now we're doing some prediction, taking a look at it. So we're actually calculating it kind of the slow way. We're taking a look at the description of the various values, and now we're going through and calculating if it's greater than 50%, then we're saying the probability is bad, taking a look at the head. And now we're down to the place of actually applying the test set and taking a look and seeing how well it did. And this is where we're going through with basically some different passes through it. So and calculating it for each one. Basically, I think we're doing 2 folds here is what this is an example of. So moving on to the easier way, using the scikit-learn's test train split, right? And this is kind of a wrapper. That's something to understand. It's a utility function there that makes life easy, and it really does. And I'm sure you guys have used it. So the basic idea here is that you import it in, and then as always, numpy is np, pandas is pd, do some setting of the display, and then we have a file that we're going to use, our good bizloan file, load it into the data frame, partition to our x and y based upon the good and bad, creating a random forest model, not doing anything with it yet, just setting it up. Now we're going to go through and do the test train split, where we're basically saying we want 25% to be the test size. We're doing random here, just setting a random seed essentially so that it's reproducible. And at that, we've just done what all that other stuff was doing, which was marginally painful. Now we can go through and actually do our fit off of our train set, and then do the prediction off of the test set, and then take a look at the accuracy, right? And it should, why is it saying accuracy score is not defined? It may be a different version of what version I have installed of scikit-learn. Or maybe I dropped an import on the floor. Oh, that's embarrassing. So anyway, accuracy is around 90% or so, with 1 minus being the error rate of around 9%. So that's actually really pretty good. 90% is generally speaking something you're going to be quite happy with. And we can then take a look, if we want to see where it's missing it, by taking a look at the confusion matrix and seeing how often it misses on which is over here is where it's a little worse, but neither one of those are horrible. So pretty useful stuff. Do one more here where we do cross validation. So the basic idea here is doing the holdout and going through and again using the cross validate feature in model selection. So we do our imports, get everything loaded up. We then load the diabetes data set and partition. Looks like we're taking 150 records. And then essentially doing a cross validate with 3 different folds, it looks like, CVs 3. So then the basic idea, lots of documentation, we can go ahead and run it through and do the training and see the results. So doing the same sort of thing on the biz loans data, create the same sort of random forest classifier, set it this time to do 5 basically folds. Take a look at some of the things that are available, and then we can see what the test scores are. And this is where I was telling you about the first fold, whatever, is pretty bad. So I'd be tempted to look into what's going on there, right? Because it's a significant difference. It would make me wonder about the order of our data. Maybe that's something that it would be worth taking a look at to make sure it's a representative and evenly distributed data. That's a little troubling that you get that much difference, right? You would expect this kind of difference, but to get that much is pretty bad. So that's it in Python. Taking a quick look and see what we've got in R. A similar sort of constructs. Again, we'll load up the BizLoan. We're again looking for 75%. Similar logic here is what the hard way of doing it, and basically create the model, running through the various, running through it, getting back our results, and then do our predictions. And a similar sort of number. It's a little different, but not too horribly different. And with that, I'll switch back and talk about Deliverable 6. So you guessed it, it's about validating a statistical model. You're still not sure what's going on with WebEx acting weird. So you're still a data scientist working in lovely Frostbite Falls. Your bank has collected a large amount of data at the loans origination and whether or not it was repaid or defaulted. As a future in a future project, your bank intends to develop predictive models to assess risk. However, there's some concerns that the models might overfit. So your manager, Paul Fries, asked you to develop one or more model to predict loan default. And so you basically are going to split it 75-25 and make sure that you use the don't test on, or don't train on your test data. So jumping back in, so basically here you're going to develop a regression model to predict the probability of default. Select one or more of the following programming languages. So pick probably Python and R. That's what's the trend has been. And you want to use both of those. And then for each one of those languages, take the given data set, randomly split it into 2 data sets, training and test. The training set's going to be 75%, test is 25. Then for each sample, create a probability of default model that incorporates variable selections, make use of a logistic regression of trees or random forest to predict the default. Make a note of the error rate for both training and test data sets. Determine whether the error rates of the training and test sets are similar. They hopefully are. If they're not, then that's kind of concerning. Interpret these results and make a recommendation on whether the model or models could safely be used by the bank. Assess whether the chosen language or models approach had any effect on accuracy. And there's no mention in these instructions of k-fold, just so you know. What do you want to submit? Basically your source code, a Word document that includes some screenshots, and also part of a memo that talks about the method of splitting the data, the models you developed, the accuracy, and comments about any differences between the model types or languages that you used. Especially digging into something if they're not the same results. You're very familiar at this point with the data about what the bad column is, what is these other fields, and so on. And so here we want to drill into the various mastery columns. Source code from multiple programming languages, accurate and well written. You guys have been doing great with that. Screenshots provided are clear and well planned and show a full understanding of accurate outputs. That's definitely been the case so far. Clear and thorough description of the method used to split the data, the models developed, and the accuracy of the training and test sets, and then clear and thorough commentary on noticeable differences in accuracy, whether the model type or language is altered. So why is it different? And clear and thorough commentary on noticeable differences in accuracy where the model types or languages altered. And if you're bored and want to do something cool, probably take a look at k-fold, right? Might be useful, but entirely up to you. So that is module 6. And then since we're here, I wanted to talk briefly, thought it was in here, or maybe over in module. Deliverables. Deliverable 7. So, insurance analysis. This is Deliverable 7. Incorporate all the modules in the course. So lots of stuff here. So you're a data scientist working in Pennsylvania insurance company. The insurance company has collected a large quantity of data regarding policies at the time of origination, whether or not the claim was filed or not, or a claim was filed. They has also collected marketing data and sales data. The bank wishes to analyze this data to learn which type of customers should be targeted. Before beginning the analysis, your manager, June Foray, has asked you to do a basically PCA on the continuous variables. At some point in the future, the insurance company might wish to develop models with the PCA or with those principal components. Therefore, they would like a recommendation on how many is a good number. Sounds a little familiar, right? The insurance company is interested in doing an SQL query from a database that will return a list of customers that are low risk. Your managers ask you to generate a decision tree that will predict auto accidents. From the decision tree output, you will determine some Bayesian rules that predict low risk. The rules need to have at least 2 variables. It's a decision tree, not necessarily a Bayesian network, but I guess they're probabilistic in nature, so you might could say it's a decision Bayesian rules. Anyway, your manager next wishes you to analyze the data sets and provide some insights and make recommendations. The insurance company wants any model used to be parsimonious. In other words, as few variables as possible. Pennsylvania Insurance offers continuous insurance policies over time. The company has collected data related to the expected state of a policy. Management is interested in the expected policy state after 36 months. Your managers ask you conduct some Markov analysis. So that sounds pretty familiar too, right? Instructions, and there's I think a couple pages of this. So select one or more of the following programming languages, and you want to do 2 so you get full credit. Do some PCA of continuous variables from the file and conduct the PCA on that data. Then select a subset of the principal components and justify your choice. Print out the coefficients for those components. Analyze each of these components that you've selected and describe them based upon the coefficients. Comment on whether or not it makes sense. So does it seem rational? Then do some decision tree. Predict loan default. Identify one or more nodes in the tree that are low risk of default. Describe the nodes as business rules. For example, a low risk person will have less than 2 traffic tickets and has a short commute to work. And discuss whether the business rules make sense. Then the fourth item is to do Monte Carlo, and this is where you're doing the 36 months. So create at least 10 simple random samples of at least 25% of your data. Your choice of using with replacement or without replacement, and we kind of talked about that. You're going to do with replacements if you're doing 10 random samples of 25%. Otherwise, you're going to run out of data. For each sample, create a probability of collision model that incorporates variable selection. This is Monte Carlo, not Markov. Sorry, I was confused there for a moment. I was trying to make sense how I was going to come around to that. But yeah, Monte Carlo. Make a note of the variables that were selected. Decide upon a list of variables to use in a model to predict automobile collisions and decide if it makes sense or not. Then validate. For each of the chosen programming language, do the following. Basically use a 70-30 split of the data into your test and training set. Use logistic regression, random forest, and or decision trees to develop a model that predicts auto incidents. Use the variable list from the Monte Carlo selection. And then validate the model by scoring both the training data set with the test data set on the model. Note the error rate of both models. Select a model that is accurate and does not overfit. So part 2 of this, and yes, it's like 4 pages of instructions, not just 2. So Markov process, this is where you're doing a policy that can be in one of 5 states. The definition and transitions are given below. Using this information, provide a matrix after 36 months, so multiply it times itself to the 36th power, I guess, or raise it to 36, and interpret the matrix in such a way that a non-technical manager can understand the information. You get some definitions. There's a little bit of, I think I may have fixed it here. There's a little confusion, I believe, in the instructions between a safe driver and a risky driver. It'll come to you as you look at it, but if I remember correctly, there are a little weirdness there, right? Make sure that you keep that in mind between standard, safe, risky, voluntary, and involuntary. So there's, if I remember correctly, it's a little bit off, but basically here's your state transition diagram, so that basically if you quit on your own, then you're likely to stay gone, just as if you get kicked out from an involuntary, you're likely to stay gone. But there's a chance that you might become a risky driver, whereas if you return from voluntary, you're likely a standard driver, which seems a little odd because it seems like you should be able to get back to safe, right? But anyway, part 3, predicting sales, use the time series data set. Forecasting, create a linear regression model that predicts the number of new insurance policy applications given the number of applications in the past. So this is the same basic lag thing that you've done before. Should be fairly straightforward. If you have any questions on it, let me know. As always, what do you submit? Your source code, always a good thing. Word document with screenshots that also includes that write-up as a report. That talks a bit about predicting collisions, basically those 3 parts that you're asked to do. Then we have the principal component analysis, Bayesian analysis, Monte Carlo analysis, model validation, then Markov process, predicting sales. Some data exploration, pretty kind of straightforward. Number of teenage drivers, age, years on on job, the policy owner, travel time, blue book of the car, and so on. And your rubric, as always, you guys will be going for the mastery. You do it in multiple languages. That's the first thing, and it's well written. You have some screenshots that are clear and well planned and show a full understanding of the accurate outputs. Then you have a clear and thorough prediction of collisions, completion of analysis and model, clear and thorough customer lifecycle analysis presented and discussed, and then a clear and thorough sales prediction, including graphs and Excel forecasting monthly policy applications for the upcoming year. So it's basically redoing what you just did over the previous 6 deliverables, but with a different data set. And with that, I'll wrap this up. As always, if you have any questions, let me know. That's what I'm here for. Stay safe, and we'll speak again soon.